Welcome to the first video in our homework help series. Today we'll be talking about spectrograms and taking a look at a couple different problems. So the first problem asks us to create a spectrogram for the following equation. F of t equals 4 sine 20t plus 8 sine 50t plus 12 sine 10t. So I'm going to switch over to a piece of paper here, and let's take a look. First thing I'm going to write down is my function. So f of t, and this t here tells me that I'm in the time domain. This is a time domain function. And I have 4 sine 20t plus 8 sine 50t plus 12 sine 10t. Alright, so there we go. So there's our function. We know we're in the time domain. And if we look at our frequencies here, we don't see any pi. So 20t, 50t, 10t. So it's reasonable to assume that we're talking about hertz. Great, because most of the plotting we do on these spectrograms will typically be in the units of hertz. So I'm going to draw myself a little plot here. I use the lines on my graph paper from behind. And my x-axis here, this will be my frequency. So frequency, F-R-E-Q. And my units here are going to be hertz. And then I have an amplitude. And I don't really need to know what this is to draw this. I'm just going to say that I have some amplitude. I could add some units if I have them, but not necessary for this. So the goal of the spectrogram is to look at a time domain signal, this function, for example, for a continuous function, and see what this would look like if we looked at it in the frequency domain. So time domain to frequency domain. And I'm going to start with my lowest value, my lowest frequency value. You don't have to, but it's my personal preference. I feel like I might run out of room here if I don't. So I have 10 hertz, 10t, and a value of 12. 1, 3, 4. 12, there we go, right there. 12, and I'm going to add a dot up here, right? So this 10 and 12 location. And some plots just stop there. I always personally enjoy bringing a line down so that I kind of see what that actually looks like. It gives me a good visual representation. Next I have 20t. We'll put this out here, call that 20, and that's my 20 hertz. And we're going to go up 1, 2, 3, 4. There we go, with an amplitude of 4, and I'm going to drop that down to 20. And then we're going to do the same thing for 50t, and we'll call that out here somewhere, 50 hertz, and we're going to have 8, 2, 3, 4, 5, 6, 7, 8, come across, and there's our amplitude of 8. And there we go. Quite the simple and easy spectrogram. So this shows us all of our individual frequencies that make this up, and it shows us all of our amplitudes. Now, we have another problem here, and we're going to get a little bit more complicated. I'll scroll down. And this problem asks us to create another spectrogram for a different equation. And this time around we'll be using cosines instead of sines. And we remember that there is a distinct relationship between the sine of something and the cosine of some value. And that relationship really is our phase. So we add or subtract 90 degrees of phase to get between sine and or cosine. So it should come as no surprise that we can use the spectrogram to represent cosines just like we used it to represent sines. That also brings about one good point, which is that nowhere in this spectrogram, anywhere in here, is that phase value. We have no idea if we have plotted sines or cosines. All we have is a representation of frequency and amplitude. So I'm going to slide my paper up a little bit here, and I'll just draw a nice little line so that we know, we're starting a new problem down here somewhere. And let's write out this equation, and it is a bit of a long one. So f of t, so again I am in my time domain here, and I have 4 cosine 20t. Then to add to that, I have 8 cosine 50t. Then I have 12 cosine 10t. And last but not least, I have 1. And I'm going to write this 1 just to be explicit here. Cosine of 20t. Now there's a couple of things I want to take a moment to point out. First, we are adding these functions together. That doesn't necessarily mean that we can't subtract these. These could be any kind of combination of addition and subtraction. There is, however, one catch to this, and you'll notice that is we have a frequency here of 20 hertz and a frequency here of 20 hertz. These are the same. So these will add together, and specifically their amplitudes, this 1 here and this 4 here, will add together. So we could, in theory, subtract 1 from 4 if this were a negative, but in the example here, these are added together. So really what we have is 5 cosine 20t plus 8 cosine 50t plus 12 cosine 10t. Great, and this is the same function. These functions are absolutely equivalent to each other, so this is exactly the same. These are equivalent. Great, so now that we have our function, let's draw our spectrogram for this. And just like we did before, this is a fairly simple task here, right? We're going to create our 2 axes. Down here we have our frequency in hertz. We have our amplitude up here. And we're going to pick something. I like starting down here again at 10. So let's go right here. Normally we would put this on a nice little scale to make sure everything lines up, but we're doing this video kind of quickly tonight. We're going to go, let's see, what is this? 10, we have an amplitude of 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's our spot right there. 12 is our amplitude, and we are going to come right on down. There we go. All right, what do we have next? Well, we have 20 hertz over here. We'll do that at 20, and I already know I have one out here at 50. I'm just going to finish that off right there, 50. So let's see, I have 20 hertz, and I have an amplitude of 5. 1, 2, 3, 4, 5. Right there, and remember our 5 came from our 4 plus 1. Okay, great, there's that. Let's put our 5 there. And then at 50 hertz, where am I? 50 hertz, I have an amplitude of 8. 1, 2, 3, 4, 5, 6, 7, 8. There is my amplitude of 8. Wonderful. So there's my spectrogram. I have an amplitude of 12 at 10 hertz, I have an amplitude of 5 at 20 hertz, and I have an amplitude of 8 at 50 hertz. Now coming back to our video, we'll see that we want to add a low-pass filter to this with a cutoff at 15 hertz. Draw the new spectrogram. So if we come back to our drawing here, I just want to write this down. We have a low pass filter, an LPF. So low frequencies pass through our filter, a low pass filter. And that has a cutoff at, what did we say, 15 hertz. So this actually kind of is a nice way to draw filters conceptually. I am going to add a little line here. This is just for demonstration purposes. We would never really draw this filter line on our plot. I'm just going to do it so that you can get a good visual idea of what's happening. So this is, let's call it about 15 hertz, right here between 10 and 20. So anything below this frequency, any lower frequencies pass through this filter. So any frequencies on this side of this filter line will pass through the filter and be maintained. Anything on this side of that filter line will be removed, or basically attenuated down to 0, or very near 0, depending on how real your filter is. So in this case, we would get rid of everything in this region, and we could redraw this, but I'm going to leave this just kind of as a little exercise for you to think about. But all we would have is just these two axes and this one single little frequency spike. And if you were to think about it, and I asked you to rewrite this equation, you could simply look at this and go, you know, I don't have any of these frequencies. All I have is a spectrogram that shows me this, and I can rewrite this. I know I have 10 sine or cosine hertz with an amplitude of 12. Now, next time around, we're going to talk about some convention for whether or not there should be sine or cosine, and what to do if we have sines and cosines mixed together. Thank you, and have a nice day.